Hello students, welcome to EPG Pathshala. I am Dr. Anjali Sharma from University of Delhi. Today we are going to talk on module Materials for Electrochemical Energy Conversion and Storage Devices Part 2 under the paper Energy Related Materials. So after completing this module, you should be able to understand direct ethanol fuel cells, approaches to PEMFC and DAFC challenges, solid oxide fuel cells and its component and design. So let us begin with direct ethanol fuel cells. Although during the last decade the electrochemical oxidation of alcohol, especially methanol in DMFC has been widely investigated, it has been shown recently that the use of ethanol is both more beneficial and convenient compared to methanol and other higher alcohols. The low boiling point and toxicity of methanol and its status of not being a primary fuel has led investigators to shift focus from methanol to ethanol, which is less toxic and less volatile than methanol. So ethanol can be produced in large quantities by fermentation of sugar containing biomass resources and is thus renewable in nature. In most of the countries, a strong distribution of network for ethanol exists. Also, ethanol as fuel has higher theoretical mass energy density than methanol. All these advantages favor ethanol as fuel in DEFC. The electrocatalytic oxidation of ethanol has been investigated at different platinum-based electrodes. For example, platinum with X alloys, where X is equals to Ru, Sn, Mo, Ir, Re or W. Among these, PtRu and PtSn were the most effective electrocatalytes for DEFC. The electrooxidation of ethanol is more difficult than that of methanol, since it is necessary to break the C-C bond for the complete oxidation. The maximum energy from electrooxidation of ethanol is obtained if the oxidation reaction goes to completion. The complete oxidation reaction of an ethanol molecule involves release of 12 electrons at anode. The reversible cell potential at standard condition of a DEFC is calculated as 1.145 volts. At a higher operating temperature greater than 100 degrees Celsius, a DEFC gives better performance with an enhancement of CO2 formation. Below 100 degrees Celsius, product analysis by chromatographic technique or by differential electrochemical mass spectroscopy provides a detailed reaction mechanism of ethanol oxidation on platinum electrodes in acidic medium. This involves parallel and consecutive oxidation reactions. So reactions occur at higher electrode potential E greater than 0.8 volts versus RHE, where the water molecule is activated to form oxygenated species at the platinum surface. Second reaction occurs mainly at lower potential E less than 0.6 volt versus RHE. There have been considerable efforts to develop bimetallic and trimetallic anode catalysts such that the complete electrooxidation of ethanol to CO2 at lower temperature is possible, and that there is no crossover ethanol from anode to cathode. The single direct ethanol fuel DEFC test at 90 degrees Celsius, 1 bar with catalyst loading of 1 mg per centimeter square and 2 m methanol as anode feed showed an enhancement of catalyst activity in following order: PT, RE, SN, where 20% PT, 5% RE and 15% SN by weight greater than PT, IR, SN or C, where 20% PT, 5% IR and 15% SN by weight greater than PT, IR, SN over C, where 20% PT, 10% IR and 10% SN by weight is greater than PT, SN or C, where 20% PT and 20% SN by weight is greater than PT, IR, SN oblique C, 10% PT, 15% IR and 15% SN by weight is greater than PT, IR or C, 20% PT and 20% IR by weight greater than PT or C, where 40% PT by weight. PT, RE, SN and PT, IR, SN or C exhibited highest performance among all the catalysts prepared with power density of 33 and 29 milliwatt per centimeter square in DEFC respectively, operating at 90 degrees Celsius. In recent years, the interest in the direct alcohol alkaline fuel cell rose again because of its better oxygen reduction kinetics in alkali than in acidic environment, simplicity, low cost and comparable efficiencies compared to other type of fuel cell. It has been reported in literature that the typical power density achieved using PTRU in ratio of 40:20% by weight catalyst at 1 mg per centimeter square is 15.8 milliwatt per centimeter square at current density of 26.5 milliampere per centimeter square for methanol and 16 milliwatt per centimeter square at 26 milliampere per centimeter square for ethanol. The typical power density achieved for NaBH4 is 20 milliwatt per centimeter square at 30 milliampere per centimeter square using PT black as anode. A mathematical model of DAAFC developed predicted the experimental data well. Oxygen reduction reaction at manganese oxide cathode in alkaline medium is studied using cyclic voltammetry and by measuring volume of oxygen consumed at cathode. Single peak in cyclic voltagram suggests that 4-electron pathway mechanism prevails during oxygen reduction at MnO2 cathode and alkaline medium. This is substantiated by calculating the number of electrons involved per molecule of oxygen reacted at MnO2 cathode from the oxygen consumption data of different fuels. A simple DAAFC stack has been developed which consists of a series of flow channels in anode and cathode chamber. Anode and cathode electrodes were used as platinum, black and MnO2 respectively. The open circuit voltage of the stack made up of 4 cells was nearly 4.0 volts and the maximum power density obtained from such a stack at 25 degrees Celsius was 50 milliwatt per centimeter square at 20 milliampere per centimeter square for methanol and 17 milliampere per centimeter square for ethanol. Now let us see what are the approaches to PEMFC and DAFC challenges. Proton exchange membrane fuel cells and direct methanol fuel cells currently use platinum-based catalysts at the anode and cathode. It would be difficult for the fuel cell technology to become competitive with other energy convergence technologies unless the overall material cost is reduced significantly. For example, Gester et al. Have reported that the approximately a one-fifth of the platinum loading is needed in PEMFC stack for mass commercialization of fuel cells powered automobiles. One method to decrease the cost of materials in catalytic layers of a membrane electrode assembly is to engineer catalysts with ultra-low precious metals loading that still meet performance specifications. Researchers are currently engineering nanostructure supports such as carbon nanotubes to increase the dispersion of the precious metal catalyst and enhance transport in active layer. Others are attempting to reduce the catalyst cost. Two approaches to reduce catalyst cost are currently being actively pursued. One is to reduce PT loading and the other is to explore non-noble catalysts. In the short term, catalysts containing low amount of platinum are the priority and are also practical, but in the long term, non-noble metals catalysts would be the better solution. Tremendous breakthrough and efforts have been made towards the finding out low platinum loading anode catalyst and non-noble metal catalyst. While other researchers have developed low metal loading nanoscale platinum bimetallic catalyst for anode of a PEMFC with much higher power density, and Lim et al. Have also developed PD-PT bimetallic nanodendrix PEMFC cathode with high activity towards oxygen reduction reaction. A team of scientists at US Department of Energy's have collaborated with researchers from the University of Delaware and Yeshiva University and have synthesized a ternary PTRH SNO2 catalyst for depositing platinum and rhodium atoms on carbon-supported tin oxide nanoparticles that is capable of oxidizing ethanol with high efficiency and holds great promise for resolving the impedance to developing practical direct ethanol fuel cells. This electrocatalyst effectively splits the CC bond in ethanol at room temperature in acid solutions, facilitating its oxidation at low potentials to CO2, which has not been achieved with existing catalysts. Water and thermal management issues should be handled in great care with new types of gas diffusion layer GDL. Example, carbon cloth or metal or carbon cloth for better electron transfer and mass transport of the reactants and products. A well-defined fluid flow path in GDL and electron transfer through solid metallic structure would reduce over potential losses. GDL is the key to the success of MEAs. It should be such that the activation over potential at anode and mass transport over potential at cathode are minimal. GDL should keep a balance between water flooding conditions, increase of mass transport resistance, hence in loss in voltage, and water drying condition where decrease of proton conductivity in membrane. So designing of thinner bipolar plates of low resistivity materials for excellent stack performance is the key to success of minimization of cost and higher efficiency as mentioned. So traditionally investigators have been giving a maximum importance to membrane and electrocatalyst development. But as shown in the figure, on cost component of a typical PEMFC stack, it becomes obvious that the commercialization of PEMFC is highly dependent on development of cheaper and efficient bipolar plates, and GDL, having high conductivity and high surface area with uniform distribution of pores. Now here on the screen you can see the percentage share of PEMFC cost components. So 11.3% is PEM, 32% is electrode, 37.4% is bipolar plate, 9% is platinum, 4.9% is assembly, and 4.6% is miscellaneous. It would be difficult for the fuel cell technology to become competitive with other energy conversion technologies unless the overall materials cost is reduced significantly. Solid oxide fuel cell or SOFCS. A SOFCS uses a hard ceramic crystal lattice instead of an organic membrane as electrolyte and operates at temperature of 650 degrees Celsius to 850 degrees Celsius. Today's technology employs several ceramic materials as the active SOFC components. The anode is typically formed from an electronic conducting nickel yttrium stabilized zirconia cermet, that is a ceramic or metal composite. The cathode is based on a mix that is both electronic and ionic conducting perovskite lanthanum magnate. Yttria stabilized zirconia is used as the oxygen ion conducting electrolyte. The development of suitable low-cost materials and low-cost fabrication of ceramic structures are presently the key technical challenges facing SOFCs. The cell is constructed with two porous electrodes that sandwich a electrolyte like YSZ. At high operating temperature, oxygen ions formed at the cathode migrates through the crystal lattice of YSZ electrolyte. As hydrogen is passed over the anode, oxide ions move across the YSZ electrolyte to oxidize hydrogen to water. The oxygen is supplied usually from air at the cathode. Electrons generated at the anode travel through an external circuit and load to the cathode, completing the circuit. Oxygen combines with electrons at cathode to form oxide ions, thus completing the reaction. SOFC can achieve as high efficiency as 80% when used to extract combined heat and power, and thus large stacked SOFCs can be used potentially as large stationary power source. The smaller SOFCs down to 2 kilowatt can provide auxiliary source for power to truck, forklift, etc. The main advantages of SOFC is possibility of internal reforming at 650 degrees Celsius to 850 degrees Celsius, and hence natural gas can be used as fuel in SOFC. The reactions given on screen occurs at the SOFC electrodes when hydrogen is used as fuel. CO2 is produced when methane is used as fuel. Solid oxide fuel cell SOFC allow conversion of a wide range of fuels, including various hydrocarbon fuels. The relatively high operating temperature allows for highly efficient conversion to power, internal reforming, and high quality byproduct heat for cogeneration or for use in bottoming cycle. Indeed, both simple cycle and hybrid SOFC reaction system have demonstrated among the highest efficiencies of any power generated system combined with minimal air pollution emissions and low greenhouse gas emissions. Combined with the ability of SOFC to use conventional fossil fuel, this could help reduce the cost of fossil fuel because less expensive materials for construction could be used at lower temperature. SOFC electrolyte. Currently, yttria stabilized zirconia in 3,8 or 10% yttria, abbreviated to YSZ, is the most commonly used electrolyte for SOFC. YSZ provides high conductivity at temperatures above 700 degrees Celsius while exhibiting negligible electronic conductivity at these temperatures. Above 1500 degrees Celsius, it becomes an electronic conductor. Alternative electrolytes have been considered and are being developed. Scandium-doped zirconia is more conductive than YSZ, permitting a further reduction of the operating temperature by 50 to 100 degrees Celsius. Gadolinium-doped ceria is even more conductive but is partially reduced in hydrogen at temperatures above 600 degrees Celsius. Formation of Ce+3 ions generated electron holes that make ceria electronically conductive, thus shorting the cell. Alternative electrodes have been considered and are being developed. Requirements of anode. Although a wide range of materials has been considered as anode materials for SOFC, most developers today uses a cermet of nickel and YSZ. The composition of the anode, particle size of the powders and manufacturing scheme are to achieve high electrical conductivity, adequate ionic conductivity, and high activity for electrochemical reactions and reforming and shift reactions. Reduction of the NiO powder in the virgin anode mixture to Ni results in the desired porosity. For the most recent anode supported cell, it also achieves good mechanical properties and maintains geometric stability during manufacture and operation. It should be noted that electrode electrolyte of a SOFC is designed as anode cathode or electrolyte supported cell. Of these, anode supported cells are more common and successful. For example, by using a combination of coarse and fine YSZ powder, mechanical strength can be ensured while also achieving the desired contact between nickel phase and the YSZ phase. In some modern cell designs, a graded anode is used to achieve coarse porosity, high mechanical strength in most of the anodes, and fine porosity in the anode zone immediately adjacent to the electrolyte. Requirements for the cathodes. Most cathode materials used in SOFC today are lanthanum-doped perovskite materials. Currently, most cathodes are based on the doped lanthanum magnetites. In high temperature SOFCs, strontium-doped lanthanum magnetites is used. The choice of this material is a compromise between a number of factors. With YSZ electrode, many lanthanum-based components form the insulating lanthanum zirconate with ceria-based electrolyte. This issue is not a concern and other cathode materials are considered. For low temperature cell, conductivity of LSM, that is lanthanum magnetite, is inadequate and other materials such as strontium doped lanthanum ferrite, that is LSF, are considered. Thermal expansion coefficients of cathode materials that closely matches with YSZ are considered. For intermediate temperature operation, say 700 to 800 degrees Celsius, a composite layer, typically 20 to 40 micron thick of YSZ and LSM, is often used to overcome the modest ion conductivity at lower temperature. Now let us see the interconnects and sealants. Broadly, interconnect materials for SOFC fall into two categories: conductive ceramics, that is perovskite materials for operation at higher temperatures, and metallic alloys for lower temperature operation. The ceramic interconnect used in higher temperature SOFCs are primarily doped with lanthanum and yttrium chromides. These perovskites are unique in that they exhibit high electronic conductivity and resist reduction under exposure to syngases at high temperatures. At 1000 degrees Celsius, the conductivities of these materials range from 1 to 30 Siemens per centimeter, with activation energy of 12 to 19 kilojoules per mole. Depending on dopant and dopant level, lanthanum chromide based interconnects have shown to be stable in cells for as much as 69,000 hours. However, one problem with ceramic interconnect is that they are rigid and weak, similar to the ceramic cells. Metallic interconnects for cells operating at around 900 degrees Celsius include high chrome alloys. Lower operating temperature would allow the use of ferrite steels that could reduce the material's cost, and ferritic steels are typically easier to process with low cost processing techniques. Design of SOFCs. First is the tabular SOFCs. The lifetime of the tabular SOFCs is 3000 to 7000 hours because of mechanical and electrochemical instability of the used materials. The electric current flows along circumference of anode and cathode causes high cell losses. Another type of SOFC design is planar SOFC design. The planar cell design of bipolar plates is easy to stack, no longer current pathways, low fabrication cost, and involves easy methods of fabrication, example screen printing and tape casting. The drawback in the planar design is thermal expansion, mismatch between ceramic and support structure, leading to problem with the gas sealing. Challenges in SOFC development. SOFC developers and research are working on materials that can provide high ionic conductivity at low temperatures like 700 degrees Celsius or below. This will significantly reduce the cost and simplify its operation at high temperatures. More challenging is to optimize cathode microstructures, obtaining higher electronic conductivity and lowering of cathode over potentials. Both tubular and planar design has its advantages and disadvantages. Tubular design gives better current density than planar design, but its cost is higher. On the other hand, the planar design has the stability of utilizing traditional and commercial accepted ceramic processing techniques like tape casting and screen printing. The main hurdle which planar design needs to overcome is the higher temperature sealant, which separates both fuel and oxidant component. Lifespan of SOFC having high efficiency needs to be increased and capital cost needs to be reduced. These can be improved only if pre-reforming is not necessary and the electrodes give considerably less over potential. Basic performance requirements indicate that the stack should be able under high thermal gradients within a cell as reforming and oxidation is taking place in the same stack. In addition to SOFC as standalone DG or in CHP system, SOFCs are being developed in an SOFC/gas turbine hybrid configuration. In the hybrid composition, the fuel cell converts fuels, for example, either direct hydrogen, syngas from fossil fuels or biofuels, into electricity and water along with byproduct heat. The residual fuel from the fuel cell is then burned by a gas turbine for additional electricity production. The product could have ranged from 1 to 10 megawatt with more than 65% efficiency, and it could be cost effective compared conventional coal and gas based thermal power stations. So students, let us now summarize what we have learnt in this module. We have studied about direct ethanol fuel cells, approaches to PE, MFC and DAFC challenges. We have also learnt about solid oxide fuel cells, that is SOFC, and studied about their components and designs. Thank you.